In this lesson, we're going to look at two important types of right triangles that are named because of the angles that make them up. We have 45, 45, 90 triangles, and we have 30, 60, 90 triangles. So each of these is a 45, 45, 90 triangle. These angles add up to 135, so this must also be 45 because the angles add up to 180. This is a 30, 60, 90 triangle. This is 30 because, again, the three angles have to add up to 180. There are important relationships between the lengths of the sides of a 45, 45, 90 or of a 30, 60, 90 triangles, which you would do well to memorize. Let me show you how we derive them. For a 45, 45, 90 triangle, because this is also 45, the triangle is isosceles. These two angles are the same, which means these two sides are the same. Let's say these are length 1 for the time being. Then using the Pythagorean theorem, 1 squared plus 1 squared equals c squared, c being the length of the hypotenuse here. This is 2. So if c is the square root of 2. So this must be square root 2. Now, if I scale this triangle up, keeping its angles the same, just making it larger or smaller, all three of these sides would multiply by some number a. So it is useful in this pattern to replace this with this number times a. So here we're going to have 1a, which is just a. This is 1a, which is just a. And this is going to be a times the square root of 2. As a side note, normally when we write a number times a variable, we put the number in front, like 4a. But when the number is square root, like square root 2, we don't want to write this because of the danger of thinking that maybe this root goes over the a as well. And so we typically write the root 2 after the a. So this is a pattern that you should memorize that works for any 45, 45, 90 triangle. These two sides are the same, represented by a, and then this is the square root of 2 times a. There's a second pattern which would be helpful to memorize, which is what you get if you take these and multiply these by the square root of 2. So we're going to multiply all threes by the square root of 2, making a larger version of this triangle. Of course, if I multiply these by square root 2, I will just get a root 2 and a root 2. And then the hypotenuse, I'll get a times the square root of 2 times another square root of 2, but that's just the square root of 4 or 2. So we have 2a here. Both of these patterns are worth knowing. This one is useful when you have a square root on the hypotenuse, and these are integers. And this one is useful if you have a square root on the two legs, and the hypotenuse is an integer. We'll see how to choose between them when we do an example problem. Now, for the pattern for a 30, so you want to memorize these. The pattern for a 30, 60, 90 triangle is come at because if you reflect this triangle and place another copy next to it, so here's a reflection of this triangle. This is also 60. That means this must be 60. It's the 30 times 2 also. So this triangle has all angles the same. It is therefore equilateral. So all three sides are the same. And because of the symmetry here, if this is length 1, then this is also length 1, which means this entire length is 2. And because the triangle is isosceles, or rather equilateral, this is length 2, and in particular, this is length 2. So this is half of that. You can see here because this is an image of this triangle and makes this triangle equilateral with all three sides the same. Then using the Pythagorean theorem, if I label this b, I get 1 squared plus b squared is 2 squared. This is 1 plus b squared is 4, which means b squared is 3. So b is the square root of 3. So this b here we're going to change to square root 3. So this is the pattern for a 30, 60, 90 triangle. The shortest side across from the 30-degree angle is 1. The hypotenuse is 2, and the remaining side opposite the 60-degree angle is square root 3. Like we did over here, it's helpful to have a variable a on all of these. So if I can multiply this by any number I want to change its size without changing its shape. So I'm going to multiply all three sides by a. So I will get 1a here, or simply a. This becomes a times the square root of 3. This becomes 2 times a. This pattern for the sides in a 30, 60, 90 triangle is also worth memorizing because you can use it to solve problems involving this types of triangles. These sorts of problems are really common on standardized tests, SAT, SAT2, like both of these, because it allows them to ask questions about triangles that you can answer without using a calculator. Let me show you some simple examples. So in this first one here, all three of these, we're just going to find the missing lengths. So I need to know what these two lengths are. So this is a 45, 45, 90. I see the 90 and I see the 45, so this must be 45. So let me look at my templates now. I don't care about this one here because this is a 45, 45, 90. This here is the hypotenuse of this 45, 45, 90 triangle. So if I look at my two templates, since this has a root 2 on the hypotenuse, I want to choose the template that also has the root 2 on the hypotenuse. That's this one. This has square root 2 on the hypotenuse. This one doesn't. So what I do then is I match the template up with this particular example. So the template has a root 2 on the hypotenuse, so this is a root 2, and it's got a on the other two sides, a and a. And just by inspection, a must be 16, which means that this is 16 and this is 16, and that's it. We've completed the question without having to do any long string of calculations, because we have memorized this pattern for what happens to the sides of a 45, 45, 90 triangle. We just figured out that a was 16, and that tells us these are also 16. Here's a 30, 60, 90 example. So this is 30, 60, 90. This must be 30. So if I look at my template, let me bring a template over here. There we go. Here's my template for the 30, 60, 90 triangle. A on the shortest side, a root 3 on the medium length side, 2a on the hypotenuse. So I'm going to just simply copy the template onto here and figure out what a must be. So this is the shortest side. It's across from 30, so this is a. The medium length side is a root 3, and the longest side is 2a. So when I look at this now, I can tell immediately, since 2a is 20, that a must be 10. So that means this is 10, and this is 10 root 3, and that answers the question. The question was, what are the three lengths of the sides of this triangle? So again, knowing the template made this very quick. One last example, slightly trickier. So I've turned it on its side, but it's still 30, 60, 90. There's 30, there's 90, so this must be 60. So the short side here is opposite the 30, so that's the short side. So comparing it to my template, this is the short side across on the 30-degree angle, so this must be a. The hypotenuse across from the right angle in my template is 2 times a. And then finally, this medium length side in my template is a root 3. So this involves a little bit more calculations. So I have 6 is a root 3. I want to figure out what a is. So if 6 is a root 3, then this is a times the square root of 3. So I'm going to divide by square root 3. So I get a is 6 divided by the square root of 3. And then if you remember, if we're going to simplify this radical to get a nicer looking answer from algebra, the way we simplify a radical if we have square root on the bottom is we multiply the top and bottom by that square root. That doesn't change the value of the fraction, but changes its appearance. So I have root 3 times root 3 on the bottom of the fraction. That's 3. And at the top of the fraction I have 6 times the square root of 3. And then finally I can reduce. Outside of the radical I have 6 over 3, that's 2. So I have a is 2 times the square root of 3. And that immediately lets me fill in these values on the rest of this triangle. That means this length was 2 square root 3, and this was double that, so this must be 4 square root 3.